Reuben Budiardja, also from the OLCF Scientific Computing Group. Reuben is a computational astrophysicist, and he's the lead developer of the code he's going to talk about here. He's also a lead developer of the HPC software tool Xalt, which he has a paper in the workshop tomorrow. And he collaborates broadly, as everyone does in this group, on many diverse codes. So targeting GPUs for OpenMP with the Fortran code.
Okay, I'm grateful for the opportunity to share our experience here. And this is the work I work with my colleague Christian Cardal at the Physics Division at Oak Ridge. And I'm going to be talking about our experience in porting Genesis, an astrophysics code, on Summit. So talk a little bit about the application. It's stands for General Astrophysics Simulation System, and we designed it for running parallel large-scale simulation, and we have scaled to hundreds of thousands of MPI processes in the past. It's written entirely in modern Fortran 2003 and 2008. It's we designed it to be modular and object-oriented and extensible. We have multiple physics solver as required to do a lot of the astrophysics simulation. Core collapse supernovae is our target application at this point. And prior to this work, it's mostly CPU-only code with OpenMP for multi-threading. So for this talk, I will talk about the fluid dynamics and the time integration solver, and we're still working on porting all the other kernels to GPU. But so this code has in the past been used to study supernova, fluid instability in supernova dynamics, and that's resulted in a few of paper. And in the past also we discovered the magnetic field amplification by one of the stability, and you can see the image there is a plots of a magnetic field after a supernova explosion, and how that contributes to the magnetization of neutron star. So recently, or in the last few years, we've been porting, refactored the code to several major subdivision. We call it basics, mathematics, physics, and just sort of take the solver at different level, and then allow us to do more thorough unit testing, allow us to do ad hoc tasks and develop mini apps, and that would contribute to this kind of work more easily rather than have a large code to deal with from the get-go. So we look at several paths on how we can use GPU. So looking at CUDA will require us to rewrite most of our computational kernel, or all of our computational kernel, and also it leads to loss of the Fortran semantics that we very much love. The thing with multi-dimensional arrays and pointers and remapping, and both of us is very well versed in Fortran, and we don't really want to go that path. So also with CUDA, then you have the rest of the Fortran code that we have to interface with, and another option is we look at CUDA Fortran, but we feel that that's kind of a non-standard extension to Fortran, although it's supported by XL and the PGA compiler. And a lot of us also work in our workstation probably with G-Fortran and the Fortran compiler. So we don't see that we can easily fall back to standard Fortran if we were to use CUDA Fortran. So the path that we end up taking is using directives in OpenMP, which retain the Fortran semantics, and as I will show later. And we found out that OpenMP 4.5 has excellent support from the XL compiler on Summit, and also has good support from the Cray compiler on Titan, 2 of our machines. So that's what we end up using. And to do that, some of the OpenMP APIs, the lower level OpenMP API, does not really have Fortran interface, but that's we go around that by writing Fortran wrappers to some of this API, and it's actually only a handful, not even a handful. So basically, the allocate device is our Fortran wrapper to call the OMP target alloc to allocate the memory on the device, on the GPU. And then we also use the associate host as a wrapper to the OMP target associate pointer, and show why this is important to us. And then, of course, there's this regular transfer subroutine, the update device and update host. So if you're familiar with OpenMP, you realize that OpenMP can do this automatically, either implicit or explicitly, when you do the target pragma. But I'll show where we want to do this because we want to make an affirmative control of our data movement, and we want to have persistent memory allocation on the device, which really required to get a good speed up. So for our case, we use value here, for example, it's just a regular Fortran array, intrinsic array, and we use the convention with using d underscore to, in Fortran, we use a type C pointer as a variable that holds the GPU address. So at the higher level Genesis, we write our kernel in terms of, we have a class called the storage form, which is basically the heart of our storage in Genesis, which include metadata, this is for storing physical units and variable names, and which is really useful for I/O and visualization. And we use this to group together related physical variables, the fluid variable or the nuclear equation of state variable. And by writing it in this form, it renders more of our computational kernel more generic, and we have kind of a more uniform, simplified code for I/O, for exchanging, ghost exchangings, for prolongation and restriction when we deal with the adaptive mesh refinement. So just a very simplification here with the storage form, we have value, basically two-dimensional intrinsic array with, on the contiguous first column is just the number of cells in our domain, and on the second rank is just the number of variables, the number of fluid variables. And some of the methods here, we have initialization, which just allocate data on the host. And then we, for this group, we add the allocate device, which basically take the form of that data on the host and allocate the same location on GPU. And then we add update device host as a method. So this is a kind of just a sidebar. Probably most of us here are familiar with it, just to make sure we're on the same page. So OpenMP maps the host variable on CPU to the device variable either implicitly or explicitly. And by default, you do copy to and from. And there's this concept of present check with OpenMP. But basically, when you go into the OpenMP target, looks at if that variable does not exist on the GPU, then OpenMP will create a new one and make copy, depends on how you define your OpenMP target. So present check, if we want to maintain our own control of data movement, you don't want it to intentionally fail, and that makes OpenMP runtime to copy data that you don't need to. So sometimes it requires the explicit association to avoid the unintentional data movement. So here's an example of how we offload our computational kernel. And this is a little bit of a busy slide, so I will try to unpack this a little bit. So the color here is done with the initialization, just basically tells you how many variables, and just allocate device will allocate, as we say, will allocate the same variable on the device. And behind the scene, we do computation to basically know the address of the GPU address of each of the variable on the device and associated with the address on the host. So that's how we can pass the value 1, 2, and then the address of the D value, the first, the second, and the third. So update device just transfer the data. So on the computational kernel itself, all we need to do is just add the extra argument to tell the kernel where the device address is on the GPU. And then we call this associate host that basically tells OpenMP, anytime you see this variable, use the device the associated device address, so that you don't need to transfer or make another map of that variable. So that avoid OMP target to actually make another map, but instead just use the address that it's given to. So what's important to note here, all that we need to change in our kernel is just really the call to associate and add the extra variable to tell us OpenMP where the computational where the data is on the device. And also on the caller, we just need to add one call to allocate device. This is another example with what we call the pointer mapping. So sometimes it's from the application perspective, you know that it's easier to address your kernel in terms of the three-dimensional array, right? Because your problem is in 3D. And in our storage form, we have it all in just 1D serialized string array. So in Fortran, you can do this sort of pointer mapping where basically you want to address one-dimensional array in terms of three-dimensional array. So and the x and y and z is just the number of cells in the x, y, and z dimension. So the next thing here, then you just pass this pointer, but then you say, okay, this is actually not a new variable. For this variable, just use the device memory location that I already have in default, right? So without the explicit association that we call the associate host, OpenMP unfortunately gets confused and try to map a new variable. So that's incur an unintentional data transfer. But just by doing this associate host, then we can, in our kernel, we can retain what I mentioned earlier, the Fortran semantics of just using a three-dimensional array, and behind the scene, OpenMP just use the device address that we give, and it actually does work, which is amazing if you think about it. And it's really helpful from the application developer perspective that I don't have to change the way I think. I'm used to Fortran, I'm used to three-dimensional array. I don't have to change the way I think in order to be able to get performance on GPU with OpenMP. So it's really productive tool. We see doing it this way. So this is the application that we run our test with. It's a Riemann problem. It's an extension of the well-known shock-to problem. It starts on the left side. It's just basically there's the two initial states: a high-density, high-pressure gas with a membrane, and a low-density, low-pressure gas. At time equals 0, you remove the membrane. A shock propagate to the right, and a rarefaction wave propagate to the left, and that's the initial state. And you can extend this to three-dimensional box where you have the initial state in a corner, and then a shock propagate also to the whole box. Just to give you a sense of what we ran our test with. So this is kind of a pseudocode of the algorithm on our evolution on the fluid evolution. Basically, there's a big loop here while time is not reaching the finish time. You compute the time step, you set the fluid, you compute the differences, you reconstruct the fluid, you compute the fluxes, you update the time step. This is a two-order Rangakata, so there's two sub-steps here, and then you do a ghost exchange for the neighboring neighbor, and then you do the same thing, and that's constitute one time step fully update. So on the GPU, again, this is almost exactly the same code, the same algorithm. The only difference is that most of this kernel is now done on the GPU, and there is an additional call to transfer the fluid from the host to the GPU, and there's a transfer back to the host for the ghost exchange, and then a transfer back to the device to do the next set of substep. So very minimal change. So this is a diagram of Summit. We already went through this, but real quickly, we set our test to what we call the proportional resource test. If you see, there's 21 physical core on one socket, and that's all interconnected with 3 GPU via NVLink. So a proportional resource will be seven CPU cores versus 1 GPU. So that's how we run our test. It's basically we have its MPI have either 7 OpenMP threads or 1 OpenMP offload thread, and we have 6 MPI per host, and this is the launcher that we use, the SRun, that we create the 6 resource set, which each resource set has 1 MPI and OpenMP per resource set. So this is how we run our test. So this is the result for the 3D scaling of the Riemann problem. 2 threads, 4 threads, 7 threads, and GPU. So as from the get-go, we get about 4 to 6 speed up from 7 CPU threads to GPU. And we run this up to about 8,000 something number of GPU, so a third of Summit, 1,200 or 1,100 nodes, if my math is correct. And we get excellent speed up going from 7 CPU to GPU, although we also get near ideal scaling with the OpenMP multithreading. So this is just kind of the timings of our different kernel. I apologize if the text is hard to see, but the first, the blue is the 2 threads, 4 threads, and 7 threads, and the green is the GPU. The first cluster is the MPI timing, and the last 2 here only on the GPU side is only the code with GPU version is the data transfer to device and to host. But as you can see, the GPU version for most of the kernel has greatly speed up compared to the 7 CPU threads. This is just to see the speed up of different kernel. So most kernel we get about 20, some kernel we get about 40 x speed up, but there's one kernel here that almost gets no speed up, which is interesting, but at this time we just haven't had the chance to dig into the kernel to look at what's going on, that this Riemann solver input almost get no speed up on the GPU. But then we need to do this on the GPU anyway, so that all the computation can be done on the GPU without moving data transfer back and forth. But so one thing that we suspect is that there's a lot of call here to min and max function and comparing the speed of the wave on the wave fan for the solution of the Riemann problem, and we were thinking maybe that those function is not yet available on the GPU, or is not yet ported, or is not yet supported by the compiler on the GPU. But this is definitely something we need to look further. Okay, this is the timing distribution of our code. You can immediately notice the 2 biggest chunk here is the data transfer from host to the device and device to host. And MPI makes up the next one, and the Riemann solver input, the kernel that did not get speed up, makes up the next one. So looking at this, of course, the first thought that came up was, how can I optimize this data transfer, right? But not even with this timing, we already get about 6x speed up. So all of us familiar with using pin memory. Unfortunately, there is not a mechanism yet in OpenMP to use pin memory, and I heard that may be coming in the future OpenMP standard. But basically, we write another Fortran wrapper in Genesis to the CUDA malloc host so that we can use pin memory strategically, and we add an option to our storage form that for some of the variables that we want to use or we want to transfer back and forth to GPU, we have a pin option equal true, which under the hood, instead of calling the Fortran allocate statement, we call our wrapper to the CUDA malloc host. So someone told me that pin memory, also known as pure freaking magic, basically. So get another 2x speed up just using pin memory from the GPU to GPU with pin memory. But as I was going through our code, I realized I actually have an intentional extra data copy to the host during debugging that I forgot to remove. So I didn't have a chance to rerun, but actually the speed up now is around 11x to 12x. But Summit was unavailable for acceptance and all that, so I couldn't rerun my plot. So even better than this. And this is just like last week, basically. So what are the implications of this work? So just to get a sense of comparison, in 2010 we had this large simulation for the magnetic field amplification with SASI, and that was on GPU only with Jaguar, not even Titan. We need to do 1024 cube cells. We use 64,000 core of Jaguar. It's about 3 seconds per time step. On Summit, now we can do that with just 64 GPUs, 11 nodes on Summit, and it's even faster. It's amazing the kind of, if you look back and now it's amazing the kind of performance gain you have just in 8 years, basically. So that implies we can do higher fidelity simulation. We can do ensemble studies with a more physically faithful resolution. And that's what we plan to do. We plan to do about 200-ish supernova simulation to observe trends in supernova dynamics, and probably tens of 3D with grid transport and a handful with spectral transport, which is even more expensive simulation. And this is the first step toward the full Boltzmann radiation transport, which basically in its full glory, it's 6-dimensional problem plus time, which still requires extra scale computing, basically. So just a few remaining issues. So we try to have a single code base with OpenMP for offload and multi-threading, and we're having difficulty because the target if clause is still problematic in the compiler that we use, which is basically IBM XL. Also, we found that having team distribute directive basically cause issue with the multi-threading. So to overcome this, we either have to have 2 code base or have a preprocessor so that we can switch easily between offload and multi-threading. It would be nice if this were resolved, but I think that's not a good. That's not insurmountable within newer version of the compiler, so that we can have a single code base for offload and fall back to multi-threading. Earlier in the project we look at a way to pipeline our data movement, and we're having difficulty because there is not an easy way within OpenMP to affect which CUDA stream we want to run with, and how we can select stream, and so we basically just abandon the approach and just go bulk transfer and computation, and then another bulk transfer. So I'm not sure what's the way to do it here. Maybe it requires more collaboration with the OpenMP standard or that sort of thing, or that's also implementation dependent. So Oscar, which sits in the standard, and I have been talking about this sort of things. And so better compiler support for OpenMP is always a good thing, especially in Fortran. We were able to use Genesis actually to test a newer XR compiler during acceptance and discover more bugs with the OpenMP support. And we are going to look at using CUDA-aware MPI for GPU direct, and that is supported on Titan, on Summit. And the benefit, whether you staging it manually on the host and do exchange, or whether you do it directly on the GPU, it seems that it depends on the message sizes. So that's required for more work on our part. So in conclusion, we found that OpenMP allows a simple and effective porting. This whole work takes about 2 or 3 months effort that I do on top of my other tasks, so it's not 2 and 3 months full time. So it's really, we think this is really a good path for application developer to port their code to use GPU. So with that, I'm happy to answer any questions.